Before the Industrial Revolution, nobody really cared much what time it was. The sun came up, you got up. It was midday, you were hungry, you had lunch. If the sun went down, it was time for dinner, time to go to bed. Well, the Industrial Revolution changed all that. As you started working in large factories, they expected you to show up on time, consistently, and if you didn't, you'd get fired. That's why tower clocks like this one were invented. This is the 1888 Grand Rapids Town Hall clock. I'm Darren. This is the Industrial Revolution, and it's about to strike two. Let's watch. We'll get into exactly how this clock works in a few minutes, but for now, just take my word for it that if you understand how this clock works, you'll understand how pretty much every clock works, even modern digital clocks. And the best way to understand how these giant tower clocks work is actually to step back in time just a little bit. Before we proceed, just to clarify, it's not entirely true that nobody cared about time. There are two groups who actually cared quite a lot. The first group were scientists, but they mostly cared about elapsed time, so they didn't use tower clocks. We may come back to their timekeeping systems another day, but for now, and maybe for the only time ever on this channel, well, let's just ignore the scientists. The other group that was deeply devoted to exact time, and they actually did build tower clocks, were the members of certain religious orders. This is where mechanical, geared clocks really got their start. These early clocks were a little bit different from what you might expect, though. This is believed to be the world's oldest surviving depiction of a clock. It was taken from the sketchbook of Villard de Honnecourt from around 1230 CE. If you're especially observant, you might notice that there's no hands on this clock. This is called a turret clock, and it told time just with the bells. At the time, no one really needed to see the face to read the time, but the tower was still essential here. These turret clocks, like most tower clocks, were powered by heavy weights hung from long ropes, and they needed a huge drop. The higher the tower, the longer the drop. This meant that you could wind it less frequently, have louder bells, or both. Now before this, people certainly did have concepts of time, and if needed, could even use things like sundials and water clocks, but few people did, since it just wasn't necessary. In the monastery, though, keeping track of time was critical. By the 5th century, many Christian monasteries began to follow a rigorous daily schedule called the Horarium, from the Latin word for the hours. When the bell strikes, you go to worship. When it strikes again, you go to work. When it strikes again, you eat. Doing things at the exact right time was absolutely critical, but was it even remotely close to being accurate? The short answer is no, it wasn't even close. These early turret clocks were notoriously inaccurate. They could actually drift by as much as 30 to 60 minutes every single day. To try to compensate for this, someone would be assigned to manually reset the clock every day at solar noon, or at least every day that they could actually see the sun. Why were these clocks so inaccurate? Well, one main reason was that they didn't use a pendulum. Instead, they were either water clocks, or they relied on a Verge and Foliot system with two counterweights, like this 1379 escapement made by Henri de Vic in Paris. Let's take a look at how it worked. The vertical toothed wheel on the left is called the crown wheel. It has an odd number of teeth, like 11, 13, or 15, and it's always an odd number. That's important. The heavily weighted rope is wound around the axle of the crown wheel, and this is what powered the clock. At the top of the diagram, the horizontal bar is called the Foliot. The Foliot has weights on each side that you can adjust in or out to change how fast it swings back and forth. The easy way to understand this, just think of figure skaters. When they're spinning, they bring their arms in to go faster and fling them back out again to slow down. The Foliot works just the same way. The Foliot was connected to the Verge, which is the vertical shaft running down from the Foliot next to the crown wheel. Two small plates, called pallets or flags, were attached to this shaft. They're set at an angle to each other, typically around 90 to 105 degrees, depending on the clock design. So how does the clock actually run? Well, from this drawing of de Vic's escapement, it's actually pretty easy to visualize it. The weighted cord wrapped around the crown wheel tries to turn it, but it's actually stopped when a tooth hits the top pallet. Fortunately, there's just enough weight that it can turn the crown wheel and force its way past the pallet. This rotates the verge and the weighted foliot, which swings the bottom pallet into place to catch the crown wheel tooth at the bottom, where it jams up again. The process repeats, stopping the swinging foliot, pushing it back the other way, and stuck at the top of the crown wheel again. And what about that tick-tock sound from the clock? Ever wonder where that comes from? That's the crown wheel hitting the pallets. Hit the top pallet, tick. Hit the bottom, tock. So why do these two pallets sound different? Why is it tick-tock, tick-tock? Well, that's pretty easy to explain, because the clocks were actually made by highly skilled clockmakers, not by musical instrument makers. They tuned the clocks to be accurate. They don't really have to be musically appealing. So now you've got this crown wheel turning at just the right speed. So how do you tell time from that anyway? Well, once you know how fast the gear is turning, you know exactly how many revolutions that gear will take per minute, per hour, per day. And from there, it's just simple gearing. So these Verge and Foliot clocks weren't very accurate. But now that you understand how they work, believe it or not, you actually understand how every clock built after them works too. Even though these Verge and Foliot clocks were astoundingly inaccurate, drifting as much as an hour a day, it didn't really matter all that much. It was, after all, the only clock in town. Time mattered to the monks a lot, but really, that was more to unite the community than anything else. The Horarium was critical to life in these monasteries, not because of the exact time of day, but rather how it recognized the role of time, mostly as a tool to maintain unity. So the Horarium wasn't really about time at all. It was, and is, about maintaining their faith and their community. By the 14th century, turret clocks in Italy began to pick up hour hands. They just had to add a bit to the gearing. And soon they actually picked up minute hands as well. And then the rest of the world quickly joined in. Their accuracy was still seriously lacking, though. These tower clock mechanisms were made of wood, like this 1829 tower clock mechanism from Samuel Terry, currently at the Henry Ford Museum in Dearborn, Michigan. They were good enough, but only really just good enough, and only until the Industrial Revolution came along. With the Industrial Revolution, large numbers of people were now working based on time rather than based on sunrise or sunset, and clocks had to be much more accurate. Two huge changes happened to improve that accuracy. First was a shift from wood to metal clockworks, like this 1898 tower clock made by Nels Johnson, also at the Henry Ford Museum. The metal gears and bearings allowed for far more accurate timekeeping and far less impact from things like changing humidity and temperature. Humidity was actually a big one in wooden clocks. Assuming it didn't completely seize up the clockworks, a change in humidity could swell or shrink the wood and actually speed up or slow down wooden clocks by several percent more on top of the hour a day that they were already off. The other big change was the pendulum. Invented in 1656 by Dutch physicist Christian Huygens, pendulum clocks quickly spread, becoming the clock of choice in the late 17th century. By this time, clocks had already improved to maybe 15 minutes of drift a day, but Huygens' pendulum clocks cut that drift to 15 seconds a day. The weight of the pendulum, called the bob, hangs from a rigid rod, creatively called the rod. Pendulums are great at swinging at very precise rate, which means the clock itself can be very precise. Around 1670, the next big innovation came along, the anchor escapement. It was invented by either English clockmaker William Clement or scientist Robert Hooke. The anchor escapement got its name because it looks just like a ship's anchor, with two hooks to connect to the crown wheel instead of the old Verge and pallet system. The anchor escapement allows for much longer pendulums, swinging much more slowly, which further improves the accuracy. It works almost exactly like the Foliot, except the long rod and heavy weight are far more precise. The falling clock weight puts force on the crown gear, just like before, which catches on the left side of the anchor. The pendulum swings to the left, tipping the anchor escapement to the right, releasing the left pallet and catching on the right. Works just like the Foliot did with the pallets, but much more accurately. The force from the crown gear on the escapement kicks just a bit more energy into the pendulum with every swing, which overcomes friction, air resistance, etc., to keep it swinging forever, as long as you remember to wind the clock weights. But how do you actually tune it? So this video is made possible thanks to the generosity of people helping out here on YouTube with super thanks, or through memberships at patreon.com/industrialrevolution, or by clicking the join button here. If you're able to help out, I appreciate it. If not, fully understand. In any case, let's get back to the video. There are two ways to fine-tune a pendulum clock. You can either very slightly raise or lower the pendulum, or you can add or remove weight to the pendulum. Physicists tell us that a pendulum always swings at exactly the same speed, based only on its length, not its weight, and many smaller pendulum clocks do in fact adjust the pendulum up and down. On these clocks, you can see the little nut at the bottom of the rod, called the rating nut. Turning it allows you to raise or lower the pendulum very slightly, adjusting the time it takes to swing. On modern pendulum clocks in your home, like a grandfather clock, you almost certainly have one of those rating nuts, and you've almost certainly never had to touch it. The temperature in your home likely doesn't vary much, so the pendulum rod likely doesn't expand or contract much. Once you've got it set up, you can just forget about it. But what if the temperature does change? Well, this clock had a way to adjust for that. These glass vials, now empty, originally held mercury. As the temperature increased, the pendulum rod would get longer, but the mercury would expand even more. If they got the design right, the expanding mercury would rise just enough to keep the center of gravity of the pendulum in just the right spot. But what about tower clocks? These were typically outside, so they could have massive temperature swings. And I have to admit, the idea of having that much mercury swinging around in fragile glass tubes is a little bit scary. This is the Great Clock of Westminster in London, probably the most famous tower clock in the world. More commonly known as Big Ben, they have a rather unique way of fine-tuning this clock. The pendulum on Big Ben weighs 683 pounds, or 310 kilograms, and hangs 14.5 feet, or 4.4 meters below the clockworks. It swings once every 2 seconds. They use chemistry and physics to deal with temperature shifts, making the pendulum rod of concentric tubes of zinc and steel, which react differently to temperature changes, allowing the swing to stay fairly consistent in all weather. Still, they do sometimes need to make adjustments. To do this, they use pre-decimalization pennies. On a small platform up near the top of the pendulum rod, adding a single penny will shift the center of mass up just enough to speed up the clock by about 0.4 seconds per day. Removing a penny will slow down the clock by about 0.4 seconds. The last big change to clocks was the gravity escapement, although it's not really that big of a change. With the gravity escapement, instead of the anchor directly connecting to the crown gear, you have a pair of long, heavy, free-hanging rods called gravity arms or impulse arms, which hang down from the top of the clock, being alternately pushed out by the pendulum, and then using their weight to give it a push back to keep it running. You can see the gravity arms clearly on this clock that we looked at earlier. And instead of the crown wheel, which had a lot of teeth on it and looks kind of like a crown, you instead have a gravity escape wheel. This wheel is really just a hub with a few, typically 3, long arms sticking out from it. Instead of catching on pallets, like earlier clocks, these arms actually catch on what's called a stop block on the gravity arms. The gravity escape wheel doesn't actually provide any push to the pendulum at all, unlike previous clocks. That push to keep the pendulum going actually comes from the gravity arms directly. And despite these changes, as you can see on this beautiful Grand Rapids City Hall tower clock, you still get the familiar ticking. So the pendulum swings to the left, raising the left arm and releasing the gravity escape wheel. That wheel spins very quickly, 1/3 of a turn, and slaps to a stop on the stop block on the right arm. Tick. Now the pendulum swings to the right side, lifting the right arm. That releases the gravity escape wheel, spinning another very fast 1/3 of a turn, and dropping onto the stop block on the left arm. Tick. Do you notice the difference? Why tick, tick, tick instead of tick, tock, tick, tock? Well, for one thing, there's usually 3 arms on the escapement. But for another, by the time these escapements came along, the machining had improved to the point that they're so nearly identical that you rarely have distinct sounds for each leg. Of course, lots of tower clocks have more than one face, and this Grand Rapids tower clock actually has 5, 1 inside and 4 outside. These are all kept automatically synchronized since they're all run on the same shaft off the same clockworks. The clockworks drives the central vertical shaft, which connects out to the set of gears on each face called the motion works, which is responsible for converting that rotation into the separate hour, minute, and sometimes second hands. And there's a few more interesting features on this clock that you've probably noticed. At the bottom, there's 2 small electric motors. Those don't actually run the clock, but just wind it. When the weights get near the bottom, the motors kick in to lift them back up. The heavy pendulum keeps swinging while the weights are winding, so the clock never needs to stop. This odd plate is called the count wheel. This is the only part of the clockworks that actually has any clue at all what time it is. When the gearing tells the clock that it's time to strike the hour, the count wheel tells the clock how many times to strike. Let's zoom in and watch it strike 2 o'clock. Each time it strikes the bell, the large horizontal bar is pulled back 1 step. When it reaches the far right, it stops. No more bells. Each hour, the count wheel will advance by 1 more notch, meaning the bar will have to pull back 1 more time, striking 1 more bell before it stops. Eventually, it'll strike 12, and then, as the count wheel rotates again, that bar will land back at the 1 position. Let's watch that 1 more time. That big wheel with the blades on it, off to the right, is called the fly, or flywheel, or governor. It provides resistance and some inertia to keep the hours striking at an even pace. Without it, the bell strikes would get faster and faster each strike within the hour. The fly keeps that even metronome-like pace to the bells. It's mounted to a friction clutch so that when the chiming stops, the heavy fly can coast to a stop. If that ticking sounds familiar, well, it should. It uses the same mechanism as your bicycle. When you stop pedaling, the friction clutch on your bike means that your back wheel can keep coasting with exactly that same clicking sound. So with the Gravity Escapement, like all other mechanical clocks we've looked at, as long as you kept it wound and well oiled, it'll keep on ticking. And it's not only mechanical clocks that work like this. Even modern digital clocks work the same way, just with a very accurate digital timekeeping signal. Instead of gearing for 4 turns of the crown wheel or 20 turns of the gravity escape wheel per minute, instead you might count millions of electrical impulses per minute. But really it's still the same, only the gearing has changed. So a clock like this is probably the first clock that people in the early Industrial Revolution ever saw. Prior to this, maybe they'd know about 2 o'clock or 3 o'clock, but no one cared. Like 3:07? What's that? But with the Industrial Revolution, people had to start paying attention to time. First you had huge tower clocks and factory clocks like this one. And then eventually you moved on to pocket watches, wrist watches, and now smartphones. That's why clocks like this is the Industrial Revolution. Hey, thanks for watching the video. Hope you enjoyed it. You can really help us out by like, share, and subscribe. Subscribe over here. and that really helps out. And comment, I love reading your comments, and I usually respond pretty quick. If you want to see more videos on the Industrial Revolution, click the playlist over here, or the one up here that YouTube thinks you'll really enjoy next. Thanks again. I'll see you next time.